next we'll see some improvements for sum check proving, and I will give the mic to Suyash.
Okay, thanks, Oana. I'm Suyash, and I'll be talking about some of the engineering optimizations that we did to sum check, specifically to Jolt, but it also applies more generally. I think Anubhav already covered this point that sum checks appearing everywhere, be it arithmetization, lookup arguments, folding schemes, ZKVMs. Everything's kind of boiling down to like one or multiple instances of sum check. And obviously this list is non-exhaustive. There's a lot of other papers or ideas that use sum check as the main primitive. Okay. So I'll just give a brief primer of why working on optimizations to sum check was becoming important. So I've put up this benchmarking example that we had in Jolt. So this is before the optimizations. So let's say you were doing this SHA-256 hashing of, let's say, either 1,000 or 2,000 hashes. Respectively, both of them cost around 3.6 million cycles, and the 2,000 hashes costs 7.2 million cycles. What we see is as the size of the number of cycles increase, the sum check contribution starts increasing. So sum check for 7.2 million cycles becomes like a 46% part of your end-to-end proving. So in 100 seconds, it's almost 47, 48 seconds that is consumed only by sum check. So we really thought improving sum check is really necessary for us to be able to get end-to-end improvement in Jolt prover. Jolt invokes a lot of sum check instances. For doing everything, it boils down to doing sum check. But I'll specifically talk about two things that are worth focusing on, two sum check instances. The Spartan R1CS and something called as shout read address virtualization. I'll not explain how we get these equations, but these are just sum check instances that we need to prove to, in the first case, prove that the R1CS expression is correct. And the second, to prove that this read address virtualization was done correctly. So all of these polynomials that you see here are multilinear polynomials. And the goal of this is to run sum check instance over these expressions. The reason I choose these two as examples is the first one is a degree 3 sum check. While the second one is a much higher degree sum check. It could be like 5, 9, 17. It's a configurable parameter in Jolt, which will then decide the degree. So the right one is high degree sum check. The left one is low degree sum check. So it's a big spectrum that we were trying to target to come up with optimizations. For L equal to 23, which is the 7.6 million cycles that we saw, we were able to get like an 11x speed up for the low degree sum check and a relatively less impressive 1.7x improvement in the high degree sum check. After implementing all of our optimizations in Jolt prover, we saw that only from the techniques from this paper, we got like a 25% end-to-end improvement. So the sum check that was 50 seconds or somewhere around 50 seconds in the previous slide is now about 23, 24 seconds. Okay. So I think Anubhav already talked about a basic primer on sum check. So I'll not go into a lot of details, but basically in sum check, what what we try to do is we prove that the sum of a product of multilinear polynomials is equal to some C. Um, the message or the round polynomial that the prover sends in every round looks something like this, where the first j minus 1 terms here are the round challenges. Sorry, this is in round j. The prover sends this univariate polynomial. So the red values R1 to Rj minus 1 are the challenges from the previous j minus 1 rounds. And then we sum over the remaining L minus j. Actually, it should have been L minus j minus 1 variables, Boolean variables. The interesting thing to note here was that in Jolt, most of the witness values, so most of these evaluations of the multilinear polynomials, are either 64-bit or even less. The sizes of the witness is generally small. Like a lot of the witnesses are even Boolean. But the challenges need to be from the entire field. So the challenges are 254-bit because Jolt uses BN254. And as soon as we go to the second round, these challenges start blowing up the instance sizes because now everything becomes 254-bit numbers. And so the main insight of all of this work is, can we somehow exploit this smallness of the witnesses so as to avoid the challenges sort of poisoning everything into these large field elements? So that's the theme of the techniques that I'll discuss. Let's go to the first technique. First couple of techniques are pretty straightforward, and they not just apply to sum check, but could more generally be useful. So for the first technique, we're calling it small value multiplication. Consider that you have, let's say, two field elements. By BB multiplication, I'm saying big multiplication. So both of these boxes are two big field elements. And I'm showing 4 limbs for each of them in red because BN254 uses 256-bit fields, use 464-bit limbs. And we know that multiplying 4 limbs by 4 limbs, we need n square multiplications. N is the number of limbs. And on top of that, we need this reductions as well because we are working in a finite field. So we need total of 2n square plus n when doing this big multiplication. If we are doing small big multiplication, the small field element just has 1 limb. So you can immediately reduce the number of limb-wise multiplications to n. And you can use Barrett reduction to get total 2n plus 1. And interestingly, when you do just small multiplications, it's just one single limb multiplication that matters. You don't need to do any reduction, by the way, in the third case, because 64-bit number times 64-bit should always be in the field. So empirically, for BN254, a small multiplication is like 36 times, if we just plug in n equal to 4 in these expressions, a big multiplication is 36 times much slower than the small multiplication. And we also see this empirically. It's 29 empirically. And a small big multiplication you can see is almost more than twice faster than a big multiplication. So the point of all this is we must really, if our witnesses are 64-bit elements, we must really think about ways to avoid these BB multiplications as much as possible. Again, this is another simple trick. called delayed reduction. We don't really need to, reduction is expensive as we saw in the previous slide. So we don't really need to reduce until you really need to. So let's say you have to compute an expression of this form, summation Ci times Ai. Ci are small elements, Ai are big elements. So it's an SB multiplication. And then you need to sum over k of such products. What you can do is, instead of reducing in every multiplication, you just keep accumulating. So instead of restricting yourself to 4 limbs, we'll keep using 5 limbs. We'll perform the sum, and then we'll perform only one final reduction, Barrett reduction. Which means the SB multiplication that we saw on the previous slide costed like 2n plus 1 multiplications for one multiplication, and times k is the number of multiplications we are doing here. And this method, we just avoid all these reductions and we do one final delayed reduction. So it's almost like 2x improvement on the SB multiplications. So it's almost like a 4x multiplication if you consider it against the big multiplications. This is particularly important for low degree sum check instances, because you'll see this expression Ci times Ai sum over them mod b appearing in the sum check round computation. But this trick also applies more generally. Also, this same idea can also be applied to big multiplication, just that you'll have to reduce more frequently. Now I'll discuss like a couple of new tricks or new optimizations that we came up with. The first one is, we are calling it as round batching. So the interesting thing about sum check, and I glossed over this in a couple of slides before, is after every round, you need to fold the instance sizes by half. And for doing the folding, you use the latest challenge that is coming from the verifier. So for example, after the first round, once you get this R1 challenge, let's say P is your original multilinear polynomial, you bind the first variable to R1 by computing this linear combination. Now we know R1 is a big field element, like it's a full 254-bit field element. So what ends up happening is, our original P had all small values. So let's say I'm just giving an example of, let's say 16 values. As soon as we bind with R1, we go to all big values, because now multiplying with R and 1 minus R1 factor, everything blows up. And the idea is, can we avoid this? Can we avoid binding this after every round? And can we defer the binding till, let's say, V number of rounds? Turns out we can. And for that, we just need to build this single multilinear polynomial that should let us compute all the V round messages. It looks something like this. The expression is very similar to the sum check, original sum check instance. The only difference is we are keeping all these x1 to xv, the first v variables, intact. So the idea of this round batching is to treat Q very similar to what we do in regular sum checks. So Q will be used to generate all round messages for round 1 to V. And you can see the round polynomial, just like we bind the original polynomials, we can also do the similar kind of binding on the Q polynomial. So after each round, we bind the Q polynomial, but now the advantage is we are doing far fewer big multiplications, and I'll show how or how much. But the expression of binding is similar. After each round, we bind Q to the latest challenge that the verifier sends. This L Lagrange term, Lagrange of Rj, it's slightly different or slightly more complicated than this 1 minus R1 and R1 linear combination that we saw for actual binding or original binding, but it's similar. It's just a linear combination with some slightly more complex form of the challenges. So this Q polynomial that we had defined acts similarly to the so the size of Q also keeps reducing by half every round after every round. So you define the first Q. From that you can compute the first round polynomial S1. Then you get R1. You bind the Q by R1 to get the next version of Q, and that process goes on. Okay, so let's come to the advantage of what this lets us do. If you look at the naive sum check for the first V rounds, most of the cost of sum check is spent in the first few rounds, because every round the instance size gets reduced by half. So the bulk of your work you're doing in the first few rounds. So it would have costed us 2 to the power L, it's the total instance size, times D square big multiplications in the naive version. But with this round batching, what we do is we avoid these big multiplications and trade them for these small multiplications. So you see, for pre-computing this Q, we only use small multiplications, because if you remember the equation of Q, all of these values, all of these multiplications, pk, are small field elements, which means you can only use, okay, I'll just quickly wrap up. So the summary of this was that the BB multiplications no longer depend on the total instance size, and you trade them for the small multiplications. And concretely, you can see, theoretically, we can get like a 50x reduction or speed up just by doing small multiplications instead of BB multiplications. I'll not go over the couple of last techniques. They are in the slides. One of them is this product of multilinear polynomials, how we can do that efficiently. I'll just skip over this. And I'll just say a couple of words about the streaming version that Anubhav just presented. We also have a similar version where we perform this round batching. So here we can see for the first W1 rounds, we do the round batching, then the next W2 rounds, we do another round batching, and so on, so as to limit the number of the amount of data the prover has to store for each of these windows. And we actually improve on Anubhav's paper by if you're doing like a high degree sum check, this D square term is the D square times whatever is this cost for the prover really blows up if D is high. We bring that down to D log D. That's a small improvement over the previous talk. And there's also a couple of other techniques I've included in the slide appendix. And thank you very much for attending.
Thank you very much. Are there some questions? Okay, I have a question. For trick number 3, when you are batching rounds, you choose value V and then you batch for V rounds. Is there some insights that you can give us how to optimize this V, or what are the trade-offs?
So if V is too large, we need we need to store this Q polynomial. So there's pre-computation cost of this Q polynomial as well as the storage cost. Typically, v equal to 3 or 4 is good enough. Even that gives us like a very decent speed up on the sum check, because most of your work you're doing in the first 3 or 4 rounds of sum check.
Thank you. Just one more question.
Related to the previous question, so with trick number 3, is it correct to say that you have, well, after you sort of delay the multiplication by the challenges, you probably have to do VBB multiplications, then V1 small bit by 1 BB, and then you have to add all of them, V minus 1. So I'm wondering if the VBB multiplications you have to do, every time doesn't like increase your cost too much. I guess that's related to how large you fix V, right?
If V is too large, then that cost can pile up for doing those delayed BB multiplications. So V equal to 3 or 4 gives this nice setup where you don't increase those BB costs. By the way, they are much less than what the naive version requires you to do BB multiplications. But V equal to 3 or 4 typically gives pretty good results.
Amazing. Thank you again. And thank you for all the improvements you have been making on SumCheck.